Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 3 for January 2023. Let's begin with the first question. Question 1. A student is asked to identify an organic liquid P and an inorganic liquid Q. P has the molecular formula carbon-6 hydrogen-12 and P is a straight-chain molecule that contains one functional group. Bromine water was decolorized when shaken with P. Identify the functional group in P, giving the possible name for the compound. Because bromine water is decolorized, we can say the functional group present is a carbon-carbon double bond, and therefore it's an alkene. And the possible names are hex-1-in, but it could be hex-2-in, it could also be hex-3-in, or it could be the isomers of these two because they can be E and Z isomers or cis and trans isomers. So any one of all these would award you the mark that was given here. In part B, Q is a group 1 halide which produces a lilac color in a flame. When a few drops of dilute nitric acid and aqueous silver nitrate are added to solutions of Q, a yellow precipitate is formed. They say identify by name or formula the ions present. Now, addition of dilute nitric acid and silver nitrate is testing for halides. You remember chloride produces a white precipitate, bromide produces a cream precipitate, and iodide produces a yellow precipitate. So this yellow precipitate is due to iodide, and the lilac flame is due to potassium. So down here, they say when a few drops of dilute bromine water are added to an aqueous solution of Q, a red-brown solution is formed. They want you to give an ionic equation for this reaction and include state symbols. Now this is a reaction between bromine water and a solution of potassium iodide. So potassium iodide plus aqueous bromine. Because bromine is more reactive than iodine, a displacement reaction will occur. We're going to get iodine as well as potassium bromide. So this is acceptable, but they asked the ionic equation, so you write that, and then you convert this to the ionic version by ignoring the spectator ion, which is potassium. So this becomes that, and that becomes that. So this is the answer that they were looking for. One mark is awarded to the species, and the other mark to the state symbols. Moving on. A portion of the organic liquid P is added to the red-brown aqueous solution formed in C1. The mixture is shaken and then allowed to stand for several minutes. State what observation would be expected, including any changes in color. Remember we had an alkene. In my demonstration, I have potassium bromide. This is the layer we have seen previously. This is a solution we have seen previously. A result of potassium iodide reacting with bromine, we get this solution, which is going to have potassium bromide as well as iodine, and it's going to be red-brown. Now, when we add an alkene to this solution, of course, this is the aqueous layer. Introducing an alkene introduces an organic layer. Now, we know iodine is more soluble in the organic layer than the aqueous layer, so there is a chance that iodine is going to transition from this red-brown layer to the organic layer, and that colorless layer is going to turn purple. However, that colorless layer is also going to react with the iodine that it's dissolving into because the colorless layer has an alkene and double bonds can react with iodine. So it will turn purple and then turn to colorless, or it will fade as more iodine is used up or as more iodine reacts. Now for this layer, it's going to lose more iodine. So I could say it's going to turn from red-brown to fade, and there is a possibility that it could turn colorless if all the iodine can go to the other side. So in my answer, I said 2 layers are going to be observed. The organic layer turns from colorless to purple and then to colorless. That is, it could also just remain faded depending on the concentration of the alkene that is added. It could be colorless or it could just fade. And then the red-brown aqueous layer changes from red-brown to fade and then to colorless. And again, this depends on whether or the iodine transitions to the upper layer. So you could say colorless, or a student could turn from red-brown to fade, and you could get the answer as well. So this brings us to the end of question 1. Let's continue to question 2. Question 2. In an experiment to measure the enthalpy change of combustion of ethanol, a student uses the apparatus we can see here. They use the beaker instead of a copper can, so we see heat transfer is going to be lower. They use the draught shield, so heat loss is going to be minimized. So we have the water, we have the spirit burner, which is there is ethanol inside, a stirrer, and the thermometer. So they say give a reason why it is important to shield the apparatus from the rods. This reduces heat loss to the surrounding, so that is the answer. And next they say draw the hazard symbol, which should be on the bottle of ethanol. We know ethanol is flammable. And again, I want to warn you guys, there are more questions coming up both in Unit 6 and Unit 3 about drawing these hazard symbols. So please watch out. You better learn how to draw them because ethanol is flammable. So I drew the hazard symbol for flammable. Moving on. In Part B, a student devised the procedure shown to determine the enthalpy change of combustion for ethanol. 150 centimeters cubed of water is placed in a beaker and its temperature recorded. The burner containing ethanol is weighed, placed under the beaker of water, and then lit. After 5 minutes, the burner is removed. Then the temperature of the water in the beaker is recorded again. The flame is extinguished and the burner and its contents are reweighed. So the students' results are as below. We have the final as well as the initial temperatures of the water. So the temperature change can be the difference between these two. And when you subtract, you get 7.3 degrees Celsius. They've given us the masses of the burner and ethanol before and after the experiment. And of course, the difference between these two is going to be the mass of the fuel or ethanol used in the experiment. So to complete the table, the difference between that is that, and the difference between that is that. Moving on. Here they say, calculate the enthalpy change of combustion of ethanol in kilojoules per mole using the student's results and give your answer in an appropriate number of significant figures and include a sign. So they've given us the specific capacity, the density of water, as well as the molar mass of ethanol. We know that Q is mc delta T. Now, if density is 1 gram per centimeter cubed, and again, I've corrected that, mass should equal to volume, not density. So here they say, if the density of the water is 1 gram per centimeter cubed, so mass of the water is equal to the volume of water, so the molar mass is going to be 46 gram per mole. So Q, because we have 150 centimeters cubed, and this is true, then the volume, which is 150 centimeters cubed, is equal to 150 grams. So the given C is 4.18, and the temperature change we calculated was that. So when we calculate, we get this. Remember, calculating gives you the answer in joules, not kilojoules. To convert the joules to kilojoules, you have to divide by 1,000. And again, I advise students to divide because if you do not divide to write the answer in kilojoules, you're going to forget when you're calculating delta H. The next step is to calculate the moles of ethanol. From the table, we calculated the mass of ethanol and we were given the molar mass. So we just divide to find the number of moles of ethanol that was burnt. And since delta H should be kilojoules per mole, it means we're going to divide that by that. So delta H is equal to negative Q over N. And again, I put negative because the temperature increased, so that is an exothermic reaction. So negative of that divided by that gives us this. And rounding off to 3 significant figures, it gave me this. And again, here I used 3 significant figures because you can see most of the data given was in 3 significant figures, so I stayed to that as well. Down here they say in this procedure, after removing the burner, there is a delay before the flame is extinguished. Explain the effect of this delay on the value of the enthalpy change of combustion of ethanol determined in the experiment. Now, if there is a delay before extinguishing, it means some of the fuel is going to burn. However, the heat generated from that combustion is not going to be transferred to the water, so it is going to be lost. So delta H calculated is going to be less exothermic than it should have been. I said some ethanol is burnt, but the heat produced is not used to heat the water, and the calculated Q is going to be lower, leading to a lower calculated delta H, and the calculated delta H is going to be less exothermic. Moving on. So the uncertainty in each reading of the thermometer is plus or minus 0.1. They want you to calculate the percentage uncertainty in temperature change in the student's experiment. The thermometer is read twice, so the percentage uncertainty is going to be 2 times the uncertainty which we have, divided by the value that is measured, times 100. And again, writing my answer to 3 significant figures, I rounded off to 2.74%. Moving on down here, they say the student repeated the experiment using the same apparatus in an attempt to improve its accuracy. The water was heated for 15 minutes before measuring the final temperature and reweighing the burner. The data book value for the standard enthalpy change of combustion of ethanol is 1367 kilojoules per mole. The teacher said that the changes would improve the percentage uncertainty in the measurement of mass and temperature, but have little effect on the accuracy of the value obtained. State how the changes in the experiment improve the percentage uncertainties in the measurement of mass and temperature. No calculations are required. So to solve this, we could heat for longer periods of time to increase the temperature change, and increasing the temperature change means the thermometer is going to measure a bigger value and the uncertainty is going to be decreased. Also, we could use more mass of ethanol being burned, meaning heating for longer, we burn more ethanol, and this could lead to a lower uncertainty in the mass of ethanol being measured. So overall, this will lead to a lower percentage uncertainty in the delta H that is calculated. And down here they say, explain how the difference between uncertainty and accuracy led the teacher to make this statement. So we know accuracy shows the difference between the experimental value and the data booklet value. You compare and see if they are closer, then we say we are more accurate. However, uncertainty shows the range of validity of the measured value. So this brings us to the end of question 2. Let's continue to question 3. Question 3. Citric acid is used as a descaler to remove lime scale from kettles and coffee machines. So this is the structure of citric acid. They say a student determined the concentration of a citric acid descaler, labeled solution A, which had a stated concentration of 200 grams per decimeter cubed. Solution A was diluted by a factor of 10, this is very important, and then used to titrate with a solution of sodium hydroxide of concentration 0.26 mole per decimeter cubed. The procedure is as below. In step 1, using a pipette, 25 centimeters cubed of A was transferred to a 250 centimeters cubed volumetric flask. The solution was then made up to the mark with the ionized water, inverted several times, and labeled solution B. So, in step 2, a clean pipette was used to transfer 25 centimeters cubed portions of solution B to a conical flask. To convert solution A to B, there was a dilution by a factor of 10, meaning 25 centimeters cubed was diluted to create a solution which is 250 centimeters cubed. So we need to know that dilution decreased the concentration by a factor of 10, so the concentration of A is equal to 10 times the concentration of B. So in step 3, a few drops of phenolphthalein indicator were added to the conical flask, and the contents titrated with sodium hydroxide. This step was repeated until concordant results were obtained. So the first question says, in step 1, the student rinsed both pipette and volumetric flask with the ionized water before transferring 25 centimeters cubed of solution A. State the effect, if any, of these changes in procedure to the concentration of solution B. The concentration of solution B is going to be lower in the pipette because the pipette is supposed to be rinsed with a solution, not with water. So the concentration is going to be lower. But the volumetric flask will have no effect because overall it means if you have transferred using a pipette that has been rinsed with the same solution into the volumetric flask, you have transferred 25 centimeters cubed. So any water pre-existing in the volumetric flask will have no effect on the concentration because you have transferred exactly 25 into that volumetric flask, so there will be no effect. Moving on. Here they say, give a reason why the student inverted the volumetric flask several times in step 1. Inversion is there to create thorough mixing so that we get a solution of uniform concentration. And then next they say, the sodium hydroxide solution was labeled with a hazard symbol we see here. So they say a student wore safety glasses, placed the burette below head height while filling it with sodium hydroxide. State why the student took these precautions. Of course, placing below the head, you prevent sodium hydroxide from spilling into your face or your eyes, or coming into contact with the skin of your face. Also, sodium hydroxide can irritate the skin as well as eyes. And down here they say, state the color change of the phenolphthalein indicator at the end point of the titration. The color is going to turn from colorless to pale pink. So moving on. So here they say the results of the student's experiment are shown. Remember, this is calculated by subtracting the two. Subtract, you get that. Subtracting this, you get that. And subtracting that, you get that. So you are required to fill up this, which I did, and that's the answer. So they said complete the table and calculate the mean titer using all concordant results. So my concordant results were that. All were concordant except the trio. So add them up and divide by 4 in order to calculate the mean titer, which I got as 28.80 centimeters cubed. And again, let me write a 0 here. So next they say, give a reason why the student did not need to carry out titration 3 and 4. I would say because titration 1 and 2 were already concordant results, so there was no need to carry out titration 3 and 4. And then next they say, give a reason why solution A was diluted before titrating it with this sodium hydroxide solution. The solution was diluted tenfold, and look at the volume of sodium hydroxide that was used as a titer. We would require 288 centimeters cubed, and that cannot be contained in the burette, so the capacity wouldn't be enough. So I said dilution decreased the number of moles per volume. If not, the titer value would be more than 50 centimeters cubed, which is the capacity of the burette. And down here they say the unbalanced equation for the reaction between citric acid and sodium hydroxide is shown. They wanted you to complete the equation as the symbols are not required. This is a reaction between sodium hydroxide and an acid. So the hydrogens are going to be lost, replaced by sodium, and then those hydrogens will combine with the left OH to form water. So we will see this is going to be 3 and that 3. Moving on. So here they say, calculate the concentration of citric acid in solution A in gram per decimeter cubed, and they want you to give your answer to 3 significant figures. They've given us the concentration of sodium hydroxide, which is that, and the molar mass of citric acid. Now, because sodium hydroxide was titrated, I began by calculating the number of moles, which is equal to concentration times volume. And this is the concentration, that is my volume in decimeters cubed. Since our aim is to calculate the concentration of citric acid, I used the mole ratio to calculate the moles of citric acid. So the ratio is 1:3, meaning the moles of citric acid in 25 are going to be 1/3 times the moles of sodium hydroxide, which gave me that. Now, this is in solution B, 25 of solution B. So the concentration of citric acid in solution B is going to be number of moles divided by the volume, which is 25 centimeters cubed, and this is what I got. So this is the concentration. So the concentration of citric acid in solution A should be 10 times the concentration of citric acid in solution B, which is 0.102528 times 10. Remember, this is going to be tenfold, and again, to take you back here, I did that. Here, I said concentration in A is going to be 10 times the concentration in B. So we can just multiply by 10 to get the concentration in the other, which I did here, and I got that. So finally, the concentration of citric acid in gram per decimeter cubed, this was mole per decimeter cubed. So to convert to gram per decimeter cubed, we have to multiply by the molar mass, and it gave me 196.85, which is rounded off to 196 gram per decimeter cubed, and that was my answer. Moving on. So here they say, using the result of the experiment, the student concluded that the stated concentration of the descaler 200 gram per decimeter cubed. State whether or not this difference in concentration would affect the use of the descaler solution to remove lime scale in kettles and coffee machines, and justify your answer. If we look at our answer, 196 is not that different from 200, so for me I said there will be no significant difference in effectiveness since the concentrations are almost the same. So this brings us to the end of question 3. Let's continue to question 4. Question 4. The alcohols K, L, and M are isomers of butane 1O, which is that. Give a chemical test with the expected result, which would show the presence of OH group in any alcohol. Now, presence of OH group, you can use PCO5, which gives you steamy fumes, or you could use sodium, which is going to give you effervescence. In part B, a sample of butane 1O is warmed with a solution of potassium dichromate in dilute sulfuric acid. State the color change which would be observed. Because butane 1O is a primary alcohol, it is going to be oxidized, and the color change is going to be from orange to green. Next they say, the 3 isomers K, L, and M are warmed separately with portions of our solution of potassium dichromate 6 in dilute sulfuric acid. No color change was observed for K. Because we know they are isomers and no color change was observed here, we can conclude that K is going to be tertiary. So here they say identify isomer K by name or formula. Based on the formula given to us here, for carbons, I can know this is going to be tertiary, and this is going to be 2-methyl-propan-2-O. That is going to be my structure K. Moving on. So they say the other isomers L and M are oxidized when warmed with a solution of potassium dichromate 6 in dilute sulfuric acid. They say complete the table to show the displayed formulae of two isomers and product of this oxidation reaction of isomer L. Because they've given us this structure here, we can see that isomer M is oxidized into an aldehyde, therefore it must have been a primary alcohol, and therefore the other should be the secondary alcohol that could be oxidized into a ketone. Moving on. So here they say give one chemical test with the expected results which will distinguish these oxidation products of isomers L and M. So we can use Benedict's solution, Fehling solution, or Tollen's reagent to be able to distinguish them. So I said to the sample, add Benedict's solution and warm. So with sample L, which is the ketone, there will be no observable change. But for the aldehyde, a break rate precipitate is going to be formed. Now, if we use Tollen's reagent, there will be no observable change with L, but there will be a silver mirror formed with isomer M. So this brings us to the end of question 4 as well as to the end of this paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.